Good reminding. Let me record this.
Oh, thank you.
You're welcome. Thank you.
Same thing to make us so confused. All right.
Let me know when you finish. We need to go ahead.
Cool. All right. Is everybody's number down, or should I wait for more so far? Because so far I'm looking at let's see, we got Santiago, Kevin, Andy, Zachary, Tigita. If I pronounce that right, I apologize. I got James, Hasatu, Natalie, David, Lisbeth, or Almonte, whichever you prefer. I don't know. Coral, Shati, Rena, Samir, Nikala. I think I do have you already. Jeremy, Olu, however you want me to pronounce that. Anna and Sarah so far. So did I leave like anybody out, or are we all counted for? Like I think I am missing. Actually, I think that's about it. It covers up the majority of y'all. But yeah, like I'm gonna start making the group chat as we speak, so like you guys can fill in the blanks for anybody else that may not be a part of it. Yeah, got you. Thank you.
Okay, are we done?
For now, yeah.
Okay, all right. Thank you very much.
Of course.
That's very helpful. And also, I think Gamma has.
Wait. Excuse me, to you, Professor. Before we continue, yeah, I apologize, Lola. I usually go with like the first 2 letters, but yeah, sure, Lola definitely works. I apologize. I didn't mean to offend you in any way. Yeah. People butcher my name too, you know what I'm saying? And like in retrospect, it's just 4 letters. I totally agree. Yes, I apologize for that, Professor.
It's okay.
All right, let me put the numbers in.
Okay, if you could mute yourself, I can start the class.
What happened?
I said if you could mute yourself.
Yes.
So I will start the class. We have a lot to cover today. Okay, thank you everyone, and feel free to stop me at any time if I confuse you. All right. So last time we were talking about functions. We said functions can be represented with tables, with a graph, with algebraic expression, or with a sets. If you have time, if you feel yourself is not strong with algebra, the first chapter is great in this book. The first chapter is great to go over, to help you to have a strong algebra skills. But for this course, we start with functions. We talk about functions. We will talk about basically 5 families of functions. Polynomial functions. Okay, finally we're here. Okay, so this course is all about functions to prepare you going to calculus class. Calculus class is all about functions. So we're going to cover polynomial functions, rational functions, exponential functions, logarithmic functions, and trigonometry functions. All right, basically 5 types. But let's start with talking about function. So what is a function, right? Last time we covered already. But today we're going to cover transformational functions and inverse functions, and the compositional functions. All right, so let's review what is a function. The definition is a little bit difficult to understand, but let's think function as a machine, right? We use a vending machine all the time. Maybe we input $1, then the machine has some buttons, so each button acts as a function. If you want a water, let's say we input $1 and we choose the button, we press the button water, then a bottle of water will come out, right? Normally, right? So that's a function. The button acts as a function. So we give the input, the function processes the input and gives the output. So the button on the vending machine is a function. Well, another way you can think of function as two sets. The first set we call domain, the x value. Let me write a function. Let me write a linear function. So everyone knows about linear function, right? We used to have y equals mx plus b from high school. And this one we can look at it as a linear function. It's a first degree polynomial function. And we will explain more later. B, right? So in the world of functions, we don't talk about y anymore. We use another notation, f of x, to speak for y. So in this case, so basically, y equals to f of x, right? So we just use a different notation to represent function. So f of x equals to mx plus b, right? We have two sets. The first set is the x value, and we call domain. So this is the first set. This set is for the values of x. We call this set domain. And the second set, the value of f of x or y, and we call range. Right? So we're working with these two sets. So f, a value from the domain to the range. Let's see this function, quadratic function, right? Or polynomial degree 2. F of x equals x squared plus 4. Given this function, we can evaluate, right? So 3 is in the domain. So what's the domain of this function? Domain is all real number. Domain is all real number. So this is the function. Domain means the value of x or possible value of x. Means this function works with all real numbers. If you give me 3, if the input is 3, I just change x to be 3. Right? So 3 squared plus 4. What does the function do? The function square the input, add 4 to it. Square the input, add 4 to it. So this is the process. So if the input is 3, square 3, add 4 to it. That's 13. If input is -2, square -2. -2 times -2 is 4. 4 plus 4 is 8. If the input is square root of 5, square square root of 5. Square root cancel each other. So that's 5. 5 plus 4, that's 9. Right. So in this case, we have 3, -2, square root 5 in the domain. We have 13, 8, 9 in the range. So two sets. So domain of this function is all real numbers. So sometimes we use this double line R to represent all real numbers. And so if we want to show the machine, the function as a machine would be like this, right? Input x, output x squared plus 4. What does the square do? What does the machine do? The machine square the input, add 4 to it. Input 3, square 3, add 4 to it. Output 13. Input -2, square -2, add 4 to it. Output 8. Okay. Evaluation of functions, we already evaluate some of them, right? We call this function value. So this is another quadratic function. F of x equals 3x squared plus x minus 5. So f of -2, we just evaluate -2. We change x to be -2. -2 squared is 4. 3 times 4, 12. 12 minus 2, 10. 10 minus 5, that's 5. The input 0, if x is 0, this is 0, this is 0, just -5. If x input is 4, square 4 times 3 plus 4 minus 5, 47. If the input is half, square half, multiply by 3, plus half minus 5. In the end, we get -15/4. Right? And we call this process evaluation of a function. And we call these guys function value. Function value at -2, function value at 0, function value at 4, function value at half. Piecewise function. Piecewise function means we divide the domain into different parts. For this function, the domain is separated into 2 parts. From 0 to 400 is one domain, and the second domain is x greater than 400. So the function says, okay, if the variable x is in between 0 and 400 included, the function value is 39. If the input is greater than 400, the output, the function is this, the linear function. Right? We say this is a linear function, we say slope. Here we say slope is 0.20 because the number before x is a slope and the x is raised by 1, so it's a linear function. And what about 39? 39 we call constant function. Doesn't change. It doesn't matter if x is 0 or up to 400. The function value is 39 all the time. So this part is constant, does not change. And this part is a linear function. Putting together, we call this piecewise function. Piecewise function. Let's evaluate some values. So C of 100, because 100 is in between 0 and 400. So the function value is 39. C of 400, well, C of 400 is included in the first part, right? So still C of 400 is still 39. C of 480 is greater than 400, so we use the second part to evaluate. That's 39 plus 0.2 times 480 minus 400. We evaluate this, we get 55. So what if sometimes we don't evaluate function with a number, but with another letter? So let's say in this case, we have f of 8. We would still do the same thing, just change x to be 8, right? Input is a, we put it in the function is this, with 2a squared plus 3a minus 1. If the input is negative a, we'll do the same, we'll follow the function. This is the framework, the function does not change. So we square negative a, multiply by 2, plus 3 times negative a minus 1. We get 2a squared minus 3a minus 1. Well, if the input is 2 letters, it's a summation of 2 letters, a plus h. We still will change the x to be the input, a plus h. Right? X will change x to be a plus h. The rest of it we don't change. Square we do not change. Multiply by 2 we don't change. Multiply by 3 we do not change. Minus 1 we don't change. Only x is the variable, so we change x. Okay, any questions? Moses?
Lola.
Oh, wow, Moses
Oh my
here.
God.
Or
So,
maybe only Moses raised his hand. Okay, anyway,
yeah.
Lola.
So I want to just pass this example B,
Yeah.
4B. So is this like the final answer? Why isn't it like a negative 2A? Oh wait,
B, negative 3a, you mean?
no. Oh, never mind.
Okay,
It's
all right.
actually, why isn't this negative 2A? But I realize A times A cancels the negative. Never mind. I'm done.
Okay, all right. Thank you. All right, any other questions? Okay, let's pay attention to D. D is like a cumbersome, right? D, we have f of a plus h minus f of a. So we have c minus a, then divided by h. So later on, I'll give this a name, but let's call it now. This is called the difference of quotient. It's very important for calculus. It gets a name. So this is for D. So this formula, f of a plus h minus f of a divided by h, has a name. The name is called the difference of quotient. Right? Difference of quotient. So this is very important. So D is very important. Well, let's see. We have of f of a plus h, right? F of a plus h, we have perfect square. We need to expand this. So when we multiply a plus h, how do we do that? Some people call FOIL, a plus h square equals a plus h times a plus h. Right? Some people call FOIL, so you multiply a with a, you multiply h with a with h. Well, we could do this. You multiply a with a, h with h. Right. So a times a, you get the first one square. H times h, you get the second one square. Then the middle term gets from this smelling face. Right. We multiply h with a with h. So that we get a 2ah. That's how we get this. A squared plus 2ah plus h squared. This is called a perfect square. And anything important in math gets a name. Perfect square. Something square is called a perfect square. So a plus h parentheses square is a perfect square. So follow this smiling face to expand. All right. So we simplify this expression. In the end, we get this. So we subtract f of a from this. What is f of a? F of a is 2a squared plus 3a minus 1, right here. So when we subtract, we see these two terms cancel. 3a minus 3a cancel. -1 minus -1 cancel. So we see f of a part gets cancelled in this subtraction. Okay. F of a in the difference quotient always gets cancelled with the subtraction. So now we're left with 4ah plus 2h squared plus 3h divided by h. See the numerator, everyone has h, right? We can factor out h. We factor out h, then h divided by h becomes 1. So left with 4a plus 2h plus 3. What do you think this way? 4h divided by h, that's 4a. 2h squared divided by h, that's 2h. 3h divided by h, that's 3. So this is the result of this difference quotient. All right, very important, that one. Domain of a function, right? For polynomial functions, so this is a quadratic function, all real numbers. So let's see this one. What's the domain of this one? We write this way, because 4 minus 4, if x equals 4, 4 minus 4 equals 0, 0 in the denominator. In mathematics, 0 cannot happen in the denominator. We will never see something divided by 0. That 4 apples shared by nobody just does not make sense. So we don't divide 0 in math. Dividing 0 is illegal in math. All right, we don't do that. We don't divide 0. So what do we say? We say x can be any real number but 4. So we use this set notation to say x cannot be 4. So what is the domain of this function? Domain of the function is x cannot be 4. X can be any other real number but 4. Because 4 causes trouble. And this trouble is to cause the denominator of the function to be 0. So what about the g, function g? Inside square root sign, x cannot be negative. Cannot be negative. We say x has to be at least 0. X greater than or equal to 0. All right, that's the notation. So the first one, so this one domains all real numbers. Oh, let's see why it says 0 from 0 to 5. Oh, this is just example. Okay, the domain of any quadratic function is all real numbers. So domain of f is x cannot be 4. Domain of g is x has to be greater than or equal to 0 or c non-negative. Okay, now example 6. Let's see how do we find the domain of those functions. Let's see the first one, a. This is called a rational function. We're going to talk about later. We're going to details later. Because x appears in the denominator, so it gets a name rational function. And g we call polynomial-like. It's not a polynomial function. We call polynomial-like. Okay. And h, of course, is a rational function because t, the variable, appears in the denominator. Okay, let's say 8. How do we find the domain of f? The denominator we can factor as x times x minus 1. Okay, question? Anybody question? You don't have to raise your hand. Okay, anytime, just go ahead. Just stop me. Okay. So the denominator we can factor out as x times x minus 1. And now we think. So now we think. Which number, what numbers cause the denominator to be 0? Because we do not divide by 0. So let's think. So we have x times x minus 1. So if x is 0, the denominator is 0, right? So that means x cannot be 0. If x is 1, 1 minus 1 is also 0. That causes the denominator to be 0 also. So we see the domain of this function is X cannot be 0, cannot be 1, but any other numbers. If we want to write in the interval notation, so this is the interval notation. We write as from negative infinity, or this is the negative infinity. This is missing negative signs. This is negative infinity up to 0, union 0 up to 1, union 1 up to positive infinity. You see, with open parentheses means the number is not in the set. So by writing this, is saying 0 is not in the set, 1 is not in the set. Right? So the domain of f is every real number but 0 nor 1. Well, let's see function g. Function g is square root of 9 minus x squared. Under square root sign, the expression cannot be negative. So we write this way. So inside the square root sign, 9 minus x squared has to be at least 0 or greater than or equal to 0. So we want to solve this inequality. To solve this inequality, we get x in between of negative 3 and 3. So what do we see? Then we see the domain is x from negative 3 up to 3, or use the interval notation. The interval notation with a bracket. The bracket means including those two values in the set. Let's see C. C in the denominator, first denominator cannot be 0. And then under square root sign has to be, because it's in the denominator, right? It cannot be 0. And under the square root sign, it has to be non-negative. So put those two together. With a t greater than t plus 1 has to be greater than 0. That means t greater than 1. So the domain of the function for C is greater than negative 1. Or we can use the interval notation. See, okay, it's a number greater than negative 1. This is the interval notation. From negative 1 up to positive infinity. Okay, any questions? That's how we find the domain. So these three basically covers different situations. These three. So make sure you understand these three examples, important examples. Sure, so because all other functions, the domain is every real number. Just for typical, those three are typical examples. Typical three situations we have to be careful with. All right, so today we're going to talk about the transformation of functions. A graph of function with function we get points, right? Then we can graph. Okay, with graph, something called a vertical line test. Okay, if we have a graph, how do we know the graph represents a function? Something called a vertical line test. If we put a vertical line, the line intersects the graph only with one point. That means the graph represents a function. Like this case, if we put a vertical line, we see the intersection of 2 points. So this one is does not represent a function. So this case does not represent a function. This case, yes. So this is yes. This is no. Right? This is a yes. This is a no. Some equations are functions. Some equations does not represent.
Professor, can you repeat that part, please?
This one, this graph.
Yeah, that graph.
Okay, something called a vertical line test. That means if we have this graph, we put a vertical line parallel to y-axis. if this line passes the graph with 2 points for this case, this graph does not represent a function. Make sense? But this graph, B,
But it does not.
because something called a vertical line test. How many intersection points you see? The line and the graph?
2.
2. If it's 2, it's not a function, does not represent a function. Look at this one. This one, anywhere you put a line, the intersection will be only 1 point, right? So this graph represents a function.
Okay.
Okay. Some equations represent a function. So the first one is a quadratic function. The B is a circle. A circle, you know, it's like an oval, right? Any vertical line will intersect 2 points. Does not represent a function. And if we can see from the algebraic expression, if we solve for y, we get a y equals plus minus, we get 2 values. For each x value, we get 2 y values. All right, that's no. That's like one person has 2 ages. Comparing those two, the first one is a quadratic function, right? The second one is a circle. It's not a does not represent a function. But it represents if we cut from here, the top part is a function. The bottom part is a function, but together is not a function. Okay, linear function. So this is a constant function. The first one is a constant function. That doesn't matter what the x number is, the y is always b. So the first one is constant function. So linear function mx plus b. Power function. Power function is this. X some x raised by n. Yes, question?
I was gonna ask, testing. Do you necessarily have to draw the vertical line on the left side or the right side?
Oh,
Or
it has to be inside, right? Because if here, it does not matter anymore. You want to put it cross the line, cross the graph.
Well, it can be on the left or right.
Yeah,
Okay.
anywhere, if anywhere, right? You see, right? That's a good point. If we put a vertical line here, that's okay, right? It's only 1 point. But if we put a vertical line here, they intersect 1, 2, 3. As long as one place,
No, boy, you.
as long as one place fails to intersect at 1 point, it fails to be a function. Great point. So let's see this chart. Okay, we have a linear. We're going to talk about linear function, power function, root function, and the first two are something called a polynomial function, and we call this one polynomial-like function. Rational function, what this book called reciprocal functions, absolute value function, step function. Sorry, step function. They're all different kinds of functions. Right, give us a function, we can graph them. Right? We can give some easy x value. We can calculate the function value, get some points. We can draw, get a graph, like this one, right? This is f of x equals the square root of 4 minus x squared. This is a top semicircle. The top semicircle. With a function, with a graph, we talk about increasing or decreasing. Increasing or decreasing. So let's see, this part, we put an arrow from left to right. If it increases, the function increases. But if we put an arrow decreases from left to right, that's decreases. So again, from here to here, that increases. And let's say these two pieces. So this part of function increases. This is a decrease. So increasing, decreasing. right? Increasing, decreasing, increasing. With functions, we can talk about local maximum, local minimum. Let's see this one. This is a polynomial function.
Professor,
Yes.
increasing and decreasing part is just like showing it. We don't have to calculate anything.
Usually, your homework, they will ask you. Let's see this example. Your homework probably will ask you, what is the interval of the function increasing, decreasing, right? That's a good point. That's a good question. We will see from A to B, A to B increases. Let's see, what's this F? F increases, right? From A to B, and also from C to D. So A to B, A to D, F increases. But from B to C, let's use this, B to C, F decreases. So usually they ask you, from where to where function increases. So in this case, from A to B, function increases. From C to D, function increases. But from B to C, function decreases. So local maximum, local minimum. So the top point, the highest point, we call local maximum. And here we see this point and this point we call local minimum. And we just assume this graph goes on forever. Imagine this goes down to negative infinity, and this end goes up to positive infinity. So those points like this, like those two on the bottom, we call local minimum. Points on the top, we call local maximum. All right, so that's the idea of local maximum, local minimum, increasing, decreasing. Average rate of function. We know one pretty good, something called a slope, right? Let's see if we have this graph. We want to find out from this point to this point, what's the average slope? So what's the average rate? So what do? We connect those 2 points. We find the slope of those 2 lines. That's called average rate of change. All right, it's the slope of the line connecting the 2 points, and that's it. You see here average speed, y2 minus y1, x2 minus x1. So here we have 2 points basically. So we have,
Professor,
yes.
would you please repeat the previous one?
Okay, hold on 1 second. Let me read this. 4s4. Which one?
One over there, yeah.
You mean this?
About the rate of change?
Yeah, right here. Average rate of change.
That, yes.
Yeah.
Yeah.
Average rate of change means, I was explaining that. Okay, so here we say 1, 2, 3, 4, we have 4 points, right? We can talk about average rate of change of those 2 points. Then we would make a line here. Or we can talk about average rate of change of those 2 points. That would be the slope of the line connecting those 2 points. Or we can talk about average rate of change of those 2 points. That would be slope of the line connecting those 2 points. Or we can talk about average rate of change of this point and this point. That would be the slope of the line connecting those 2 points. Then let's see one example. So we want to find average speed in between of those two from time 1 2 times 4. That would be S4. So we'll get 2 points, 1 S1, 4 S4. That would be S4, treating this as x2, y2, x1, y1 would be y2 minus y1. S4 minus S1. Then x2 minus x1 will be 4 minus 1. So we evaluate, use the function to evaluate. S4 equals to 200, S1 equals to 50. Then 4 minus 1 is 3. So 150 divided by 3, we get 50. So this is the average speed between 1 and 4. All right. This is one example. Where's the function? Oh, it says given. It is given. Okay, so right here, average rate of change. So basically, we want to try to find, we have x value A, we have x value B. What's the average rate of change from A to B? So we would evaluate f of B, f of A, subtract, then divide by B minus A. So that's the slope of this line. That's the slope of this line connecting those 2 points. Let's see this example. The function is given as x minus 3 squared. We want to find average rate of change from 1 to 3. So what do? We find f of 3, then subtract f of 1, then divide by 3 minus 1. So f of 3 equals 0, because 3 minus 3 is 0. 0 squared is 0. F of 1 is 1 minus 3, that's negative 2. Negative 2 squared is 4. So 0 minus 4, that's negative 4. 3 minus 1, that's 2. Negative 4 divided by 2, that's negative 2. So average rate of change in between of those 2 points is negative 2. Right? So f of 3, so 3 is here, 1 is here. That's the slope of this line. Right? That's the slope of this line, connecting those 2 points. And also similarly from 4 to 7, we can find the average rate. That's the slope of this line. We still use the same strategy of 7 minus f4 divided by 7 minus 4, which is 5. Same thing for these life applications. That's the average rate of change. Well, sometimes linear functions have constant rate of change because it does not change. Because we have, see this function. Think about y equals to 3x minus 1. The slope, the rate of change is always 3. So linear function has constant rate of change. That means the rate of change does not change. Constant means it does not change. Because it's not changing. It's 3 all the time. And we can evaluate from those A, B, C, 3. From 0 to 1, we will get 3. From 3 to 7, we get 3. From A to A plus H, we also get 3. Right. This is the proof of that. Okay, transformations of functions. So transformation we have 2 kinds. We have a vertical transformation and a horizontal transformation. Or vertical shift, right? Vertical shift. Think about, we have y-axis, we have x-axis. So the shifting can go upward, the shifting can go downward. These two called vertical shifting. Or the shifting can go to the left or can go to the right. Those two we call horizontal shifting. Okay, so let's talk about the vertical shifting first. Let's say we have a function f of x. Then, and if another function is f of x plus c, that's a shifting of c units. If it's minus c, it's shifting negative c units. So if c is positive, this is going upward. So this function, so another function, so push f of x c units up. So this is pushing f of x down c units. So this is vertical shifting. vertical shifting always have this kind of some function adding a constant number or some function subtract a constant number. Let's see this one. If the glue line, the glue wiggle, glue curve, blue curve is f of x, where plus c is another function. That means shift this curve up c units everywhere at every point. Same thing, you can push in f of x down c units. That makes another function. And we call f of x minus c or plus c a transformation of vertical transformation of f. Let's see examples. Let's see we have a function f of x equals x squared. And it's this blue graph. Then think about another function, g of x is x squared plus 3. Because it's a plus 3, so you basically push x squared, f of x equals x squared, 3 units up. 3 units up. Same thing, if we minus 2 from x squared, that's pushing blue graph down 2 units. All right? So this is a vertical shift. Vertical shifting. Horizontal shifting. Horizontal shifting is this, in this case, it's f takes x plus c or x minus c as the input. This is sometimes a little bit difficult to see it. So this is saying changing x value, right? If it's a minus c, then changing x value to the right. This blue one is original f of x. F of x minus c, it's pushing c to the right. It's pushing f to the right, c units. If it's a plus, so imagine c is a positive number, okay? Assume c is a positive number. If it's a plus c, it's pushing the graph f of x left. This is a little bit of anti-intuition because here we see vertical shift, adding is pushing up, subtracting is pushing down. But here, adding is pushing to the left, subtraction is pushing to the right. Let's see an example. So if f of x equals x squared is the original function, is this. So let's think about g of x. G of x equals x plus 4 squared. Right? So how can we think about the g? We can think about the g in this case. So g of x equals to f takes x plus 4 as input. Right? Because the machine G is saying square the input. Square the input. Right? So G is saying add 4 to x, then square. So f of x plus 4 is square the input. It's indeed x plus 4 squared. What about h? We can think of h as f of x minus 2. Right? What's f of x minus 2? Square the input. If the input is x minus 2, square the input. That's h. That's h, x minus 2 squared. How does the graph change? Let's see these two. So the blue one is x squared. Add 4 to it, add 4, f takes x plus 4. So g, what is g? G is pushing f of x 4 units to the left. H is pushing f 2 units to the right. Subtraction is pushing to the right. Addition is pushing to the left. This could be confusing sometimes. Well, let's see this function. So f of x equals square root of x minus 3 plus 4. Let's think about y equals the square root of x. So let's think about y equals the square root of x. And f What's f? F of x can be written as, oh, this is y. They don't use the g. Let me change. Let me see if I can change to g. Okay, let's call this g of x. Okay, if that's g of x, I can write this one as g of, oh, still different. Okay, let me not confuse you. Let's not write. Let's just follow the book. Okay, so y equals square root of x, because the domain of x starting from 0. And what about this one? What's the domain of this function? It has to be non-negative, so x has to be at least 3. So x has to be greater than or equal to 3. Right? So x value starts from 3. Starts from 3. That's this one. And then add 4 to it. Right? Add 4 to it. I think it starts from 4. So we could see this function f is pushing this y, square root of x, 3 units to the right, that's minus 3, and 4 units up, right, vertical shift. So 4 gives us vertical shift. And this negative 3 is a horizontal shift. So plus 4, so add 4, vertical shift. This x minus 3 is horizontal shift. This is x minus 3, then plus 4 to the square root of function, to vertical shift. But this one only has horizontal shift, right? X minus 3. So this graph is saying push y 3 units to the right. And then again add 4, so push this blue line 4 units up. So this one contains both transformations, vertical transformation and horizontal transformation. So reflecting the graph, right? So y equals to f of x. If we have a graph like this, if we put a negative f of x, so it's a symmetric with this one, with the line of symmetry of x-axis. Similarly, if this is the f of x, if we negate negative x, there will be reflection over y-axis. Let's see these two examples. Let's see f of x equals negative x squared. If we reflect f, we see, okay, equals to the negative f of x, that would get positive x squared, right? We would get a graph of this. So f is negative x squared, and then negate, so negative will be positive, will give this piece. And if we have square root of negative x, that would be this graph. Square root of negative x would be this graph. If we negate x, negative x will be positive x. We will get this part of the graph. So this is another kind of transformation. This is reflecting over x-axis, reflecting over y-axis. Another transformation is a stretching or shrinking. It's called dilation. Right? We multiply the function by a number, we can stretch. Depends on the number, if it's bigger than 1 or smaller than 1. If it's bigger than 1, we stretch the function, make the function higher. If the number is in between of 0 and 1, it's smaller than 1, it's a shrinking to make the height of the graph shorter. Okay. So those are 3 transformations. Let's see this function. So this function includes 4 parts basically. So this x minus 3, let me write on the side. So x minus 3 gives horizontal shift, right? Horizontal shift to the right, 3 units. That's from x minus 3. Then we have this multiplied by 2, is scaling. So multiply by 2 is the stretching. Stretching. And then add the negative sign. So this negative sign is a reflection. See this negative sign? That's a reflection. Then add 1 to it. So this is adding 1 to it. This is horizontal. I mean, not horizontal, vertical. So this is 1. 1 is vertical shifting, right? This is a reason, because this is basically add 1, right? Plus 1. But if 1, we start with 1, we don't have to write plus. So this 1 is a vertical shifting up. So x minus 3 is a horizontal shifting to the right 3 units. Then 2 times this function. 2 times this function is 2, stretching this function twice as big. The negative sign is a reflection over x-axis. Then this positive 1 is pushing the graph, is vertical shifting up 1 unit. So let's see this one. So let's treat y equals x squared. Let's start from y equals to x squared. Well, y equals x squared is this graph. Now let's minus 3. Let's see x minus 3 squared, x minus 3 squared. X minus 3 is pushing this x squared 3 units to the right. Right? So now we have this purple one. Now let's do minus negative 2. Multiply negative 2. What maybe you multiply by 2? Well, let's multiply negative 2. Multiply by negative 2 is this one, becomes this one. Right? Because multiply by negative 2 is a flip over x-axis. Flip over x-axis. Then 2 stretches the height of this one. So it becomes skinnier. Because everywhere it becomes taller. So this is the negation of 2 double of x minus 3. Then we add 1 to it. When we add 1 to it, we'll push this one up 1 unit. So this one, f of x, is the red color. Is this red color graph. Okay, any questions? So this one is pretty complicated. If you can understand, try to convince yourself to understand this. Any questions?
Sarah asked on the chat, when will homework 2 be posted? And
I
when
will let you know. I will let you know. Yeah, let's talk about, do we have questions over this with transformation? Okay, if not, basically we finish about the transformation. So this is a perfect example. Okay, make sure you understand example 6. This is a super important example to understand because this including all these transformations, 3 kinds of transformations. Even an odd function, all right, there's a definition to follow. So even function means this. Means f of negative x equals to f of x. That's the definition. That means if we input negative x, is the same as input x. So example to remember is this example. F of negative x equals negative x squared equals to x squared. Okay, so x squared is an even function. Odd function means this. F of negative x equals to negative f of x. All right, that's the definition of odd function. An example to remember is x cubed. F of x cubed, f of x cubed is an odd function. Okay, x squared is always even, right? The x cubed is odd function. All right, remember these two examples. X raised by 4 or x raised by any even number is even function. X raised by any odd number is odd function. We can check this one. So a is an odd function. Right? If we plug in negative x, we see we get negative f of x. So it's an odd function. G is 1 minus x raised by 4. When we input negative x raised by 4, we still get x raised by 4. So it's an even function. And let's see C. C is neither. C, we don't get, so h of negative x is not h of x, also is not negative h of x. H is neither even nor odd. So all the functions might be odd function, might be even function, or might be neither. So how do we check? We use the definition. All right. Now let's talk about the homework. Let me mark the numbers of homework. Okay, so today, so for domain, maybe I'll leave you some. Yeah, we covered the domain already. You have already done the homework for domain. So homework will be 2.5. Let me also write this down. I'm going to post for all the homework. I'm going to post Blackboard under content. Okay. So homework 2.5. Okay, 19 and 20. 23, 27, 37 and 38. 37 and 38. Right, so for 2, Thank you. Combination functions. 8. This one is good. So 62, let me see, 61. Right. So 1, 2, 3, 4, 5, 6, 61, and 62. And that's it. 1, 2, 3, 4, 5, 6, 7, 8. 8 questions for homework 2, okay? Okay, great. Yeah, I will also post on Blackboard. Okay, any other questions?
Can you go over homework 146?
Homework 146.
Also, extreme side note for all that still didn't do it. Put in your Instagram name if you have it. I need like all of you guys in this group chat so that way we're all on board. You know, just a little footnote if you guys didn't do it. That is still up. So yeah.
Yeah, you may not get full credits because so this homework we'll do next class. If you finish on time, you get full credits. Even you don't do the question right, as long as you show me you tried. All right. But of course, don't send me only with numbers. Oh, hold on a second. Yeah, maybe I choose 2 questions from this. So 2.4, add 2 questions from 2.4 just to practice. 18. 18 and 20. All right, add 2 questions. So 2.4, 18, and 20. Yeah, I give 1 week to finish the homework. So you are right, next Wednesday. So which page? So okay. 46 on the domain, I remember. Can you tell me which page of the question? Domain, this is graph.
I think it was like 149 or something like that.
149. Oh, I mean, tell me which section.
Oh, section.
Yeah. 2.2?
I think so. Or 2.1.
Let's see the function, or maybe 2.1. You're right. Okay, is this the question? F of x equals x squared plus 1?
Yeah.
Find the domain of the function. Okay, let me show. Can you see my screen? 46, the question.
Yes.
Okay. Okay, so the x is given, right? The domain, you see the domain here is given from 0 to 5. Oh, this is weird. Find the domain of the function. Yeah. So if without this, the domain would be every real number. But now, this is limited. So what's the domain of this function? It's just going from 0 to 5. And that's it. It's written here. Just for us to try to remember this. Or you can write as the notation of integer notation. You can write this way. But this domain is restricted. So what is the domain of 45? It's from -1 to 5. But if without this, the domain would be every real number. But however, momentarily, it's restricted with this domain. Make sense?
Yeah, I think I got it. Thank you.
You're welcome. Okay.
Hello?
Any other questions?
Yes.
Yes.
So this homework 2, it's due this Friday or next week?
Oh, so 1 week? So 2.4, 2.5, right? So 1 week, which means next Wednesday. Not next
Right.
Wednesday, the before class, Tuesday. Try to finish Tuesday so you get ready for Wednesday. Next class we're going to present. I mean, not next class, next Wednesday. So this
Is it there like
homework
is there
two.
like
I'll write on Blackboard also. All right, the details.
okay. Is there a session for this class this Friday?
Yes, we meet on Wednesday and Friday from 11:30 to 1.
Okay. I would like to let you know that this Friday I might not be able to make it because I have to go to the doctor.
That's okay. That's okay. So every class I'll record. You can watch the recording.
Would that affect like my attendance grade?
No more attendance grade because
Okay.
yeah, no more attendance grade. But you have to present. All right. Any other questions?
Thank you.
You're welcome. Oh, the homework, right. The homework yesterday, I did raise flags to some students because, once I raise flag, you finish, you still have time to finish. It's due every homework. The homework I give you 1 week due. Okay, so before the class. So before, let's say before next Wednesday. So some of you get nervous, which you finish your homework, which is great. Because usually I raise the flag 1 day ahead. I should say late homework, it's getting late. You're not missing homework yet. You were not missing homework yet for yesterday. Yeah, I will. You know what? I will make because so many changes. So I will make. I will write. I will write another one already in details about homework. All right. I'm sorry for not being so clear because I'm trying to change things as easier as possible for everybody. Now let's do homework due before Wednesday, Tuesday night. Okay, so try to finish before Wednesday. So this homework try to finish before next Wednesday. Just before Wednesday. Okay, it doesn't matter how late on Tuesday. All right, any other questions? Right, you can prepare yourself to present homework from next class. All right, from when we meet on Fridays. Any other questions? Okay, if not, I see you on Friday then. You still can present homework 1 if some people want. So we'll present from Friday. Maybe not everyone get a chance to present because we really have limited time, class time. But you will get a chance because we have 1 semester to go. But when you present, make sure you understand. Make sure, yeah, sometimes I ask questions. Make sure you totally master the problem, the question. All right, I see you on Friday then. Have a good day.